Let's take a look at one of the most fascinating experiments in all of quantum physics. Suppose you have a source that fires particles, one at a time, toward a wall. The wall has two narrow slits cut into it, and beyond the wall, a screen that shows exactly where each particle lands. You send particles in, wait, and you look at the pattern they leave behind. You can run this experiment with anything small enough to fit through the slits, which in our case, we'll say are a couple hundred nanometers wide and only a few hundred nanometers apart. You can run it with light or many different small molecules, but in the early 20th century, physicists ran it with electrons. Although tiny, electrons do have a little bit of mass, about 9 × 10⁻31 kilograms, and they carry a charge. Every piece of classical physics treats them as particles. They are small, definite objects on definite paths that can be found at one exact point in space. Given this information, we might expect that firing electrons through these two narrow slits would produce two thin, well-defined sets of impacts on the back wall. But when you turn on the source and watch the screen fill in, this is what actually appears. Not two clusters behind the slits, but instead stripes, alternating bright and dark bands, evenly spaced across the screen, built up one electron at a time. These dark and light stripes are actually a characteristic property of waves. To see why, let's set the electrons aside for a moment and just run a wave through the same apparatus. Think of a sound wave moving through air, or a water wave rippling across a pond. A wave reaching the wall doesn't pick a slit. Instead, it hits both at once, and each slit becomes a new source, radiating a fresh wavefront. The result is two waves traveling toward the screen. So why do these two new wavefronts produce stripes, instead of just spreading the wave out evenly across the screen? To see why, let's start by picking a single point on the screen, and we'll call it P. Let's call the distance between the slits S, and the distance from the slits to the screen D. The two waves leave our slits, travel some distance D, and interact with each other on their way to P. Whatever the screen does at that point depends entirely on how the waves interacted between slit and screen. And since each wave passing through the slit acts as a new source, we can simplify our apparatus and just model two wave sources where our slits are. Let's start with P at the center of the screen, directly across from the midpoint between the slits. We can construct two right triangles to measure the distance from each slit to P. The first leg of each triangle is S/2, and the second leg is just D. Since both triangles have the same leg lengths, we can conclude the hypotenuse lengths are also equivalent. Since the waves travel the same distance to point P, every wave peak from the upper slit lines up with a wave peak from the lower slit. The result is that the waves constructively add to each other, forming a wave with twice the height of each wave on its own, which leads to a bright band on the screen. Now let's move P across the screen. As P shifts, the path lengths are no longer equivalent, and the two waves start arriving slightly out of step. As we keep moving, we reach a point where one wave is arriving exactly half a wavelength behind the other. Every peak from one slit lines up with a trough from the other. Here, the waves destructively interfere and the sum goes flat, creating a dark band. Finally, as we keep moving P up, the offset grows past a half cycle and on toward a full cycle. As we approach that full cycle, the waves are again in phase, constructively add to each other, and produce another bright band. That's the whole pattern. Every point on the screen sits at a slightly different pair of distances from the two slits, so the two waves arrive there at a slightly different offset. Where the difference in distance traveled by the two waves is 0, or an integer multiple of the wavelength, the result is a bright band. And as we approach distances where one wave travels half a wavelength longer than the other, the result is a dark band. Now let's put it all together. Instead of walking a single point across the screen, let's send a continuous supply of waves through the slits. The result looks like this. The bright and dark bands we traced out by hand appear exactly where we predicted and create this characteristic wave pattern. Now let's compare that to a simple particle. A particle has to pick a slit. It goes through one or the other, lands on the screen, and leaves a dot directly behind whichever slit it took. Fire many of them, and what you get is two impact clusters. No stripes, no interference, just the shadow of the slits projected forward. Let's go back to the electrons specifically now. You'll recall the pattern they gave us had similarities to both the wave and particle results. The electron's impacts created striped bands similar to the wave result, but the pattern was built up one electron at a time, similar to the particle result. Whatever's happening at the slits isn't strictly wave or particle behavior, it's a strange mix of both. So in hopes of figuring out exactly what's producing the electron pattern, we can add some components to our experimental setup. We'll place a detector across one of the slits, which we will denote with this little box. The detector is simple, a thin beam of photons running across the slit opening, and a sensor positioned to catch any photon that scatters. When an electron passes through that slit, it knocks one of the photons off course. The sensor registers it, and we get a click. This gives us a real test. If the electron is a particle, it goes through one slit or the other, so we should hear a click on roughly half the runs and silence on the other half. But if the electron is physically passing through both slits at once as a wave, then part of it is always at the instrumented slit, and every single electron should trigger a click. So we run the experiment again. And shockingly, the stripes disappear completely, and our detector registers a hit 50% of the time. What's left is two clusters, one behind each slit. The same pattern classical particles would have produced from the start. Nothing about the experiment changed, except that we now have a record of which slit each electron went through. We didn't block a slit, change the source, or modify the screen. The only thing we added was that record. And that was enough to take the wave behavior away. As a brief aside, this result is where a lot of people are tempted to reach for something mystical. The story usually goes that the electron somehow knew it was being watched, and the act of looking is what collapsed the wave behavior. But let's zoom in on when the collapse actually happens. It turns out that the instant the photon bounces off the electron, the wave behavior disappears. Not when the apparatus records a result, and importantly, not when someone reads it. This has been proven by a class of experiments called quantum eraser experiments. We won't cover those experiments now, but the important thing to realize here is this. The wave behavior doesn't care who looks. It cares whether the information about which slit the electron took exists. When that information is preserved, even in a single scattered photon that nobody will ever measure, the stripes vanish. And when that information is destroyed, the stripes return. Consciousness has nothing to do with it. Information does. So at this point, we know that the electrons in our experiment are acting somewhat like waves and somewhat like particles. When we try to find out which, the wave properties vanish. This naturally leads to some deeper questions, like what's actually doing the waving, and why does an electron even have a wavelength to begin with? Let's start with the first question of what is doing the waving. One of the stranger things we noticed about the electron's behavior was that they created stripes on our screen, the way a wave does, but they created those stripes one impact at a time, the way a particle would. The critical observation here is that the particle impacts themselves were distributed across the screen in the same places you'd find the bright stripes from a wave. More precisely, where the intensity of the bright bands was high, there was a high probability of an electron landing there, and where the intensity was low, we were less likely to find an electron impact. Graphically, that would look like this. On the y-axis, we show the probability of impact, and on the x-axis, the position on the screen. Physicists call the property that our electrons are exhibiting psi squared, or the probability density. That is, how likely it is to find a particle in a given location when you actually make a measurement. The underlying quantity here is called the amplitude, or wave function, of the electron. That's the one real difference between an electron and a wave of light passing through the same slits. With light, the wave is a real physical field. Its squared amplitude is the brightness you see on the screen, painted on in a smooth, continuous fashion. With an electron, the wave properties tell us about the probability. Its squared amplitude is the chance of where the next dot lands. One electron gives you one dot, placed at random, weighted by psi squared. But run thousands of electrons through the slits, and the dots pile up into exactly the shape of our probability density function. Looking at the graphs side by side, the curve is the same, but what the curve means is different. For light, the curve is the picture you see. For the electron, the curve is the distribution rule the impacts obey. This also explains what we mean when we say the wave behavior collapses. When nothing in the universe records which slit the electron took, psi is spread across both slits, and our probability density interacts with itself, creating fringes. But the moment a record exists, our probability density function loses its spread and collapses to a bump behind each slit, with nothing left over to interfere. The stripes don't fade out for a mysterious reason. The probability density function just doesn't allow them to be anywhere but directly beyond the slits. So the answer to our first question here is the waving is really just the wave function of our particle interacting with itself. It's not physical in any sense, but instead tells us about the probability density distribution. The next question is where that probability density comes from, or more generally, why does an electron have a wavelength to begin with, and what sets its scale? To get there, we again need to step back from electrons specifically and look at something every piece of matter has in common. Momentum. Anything that moves and has mass is guaranteed to have a non-zero momentum, whether it's an electron, a baseball, or a planet. And in 1924, Louis de Broglie made a claim that turned out to be fundamental in understanding the electron behavior we just observed. He claimed that every piece of matter with momentum must also have a wavelength, and that wavelength is set by one tidy expression. Lambda equals h over p, where lambda is the wavelength, h is Planck's constant, and p is the momentum. Planck's constant is tiny, roughly 6.6 times 10 to the negative 34th joule seconds. And because it's tiny, the wavelength of anything you can hold in your hand is going to be extraordinarily small. But let's see what happens when we run the electron from our experiment through this formula. You may recall from the beginning of this video that an electron's mass is about 9 times 10 to the negative 31 kilograms, and in a typical lab setup, electrons might be accelerated to around 1,000,000 meters per second. To find the momentum, we can simply multiply these values together. Then, dividing by h, we find that the wavelength comes out near 1 nanometer. Because our slits were a couple hundred nanometers wide and a similar distance apart, the electron's wavelength was on roughly the same scale as the apparatus, and so the interference pattern is large enough to resolve. The important takeaway here is the electron's wave behavior isn't exotic. It just happens to be visible in our experiment, providing us a type of window into the quantum world. Now let's try the same calculation with a baseball. Call it 150 grams, thrown at 40 meters per second. Calculating the momentum, we find it's enormous compared to the electrons, so the wavelength is the inverse. We get something near 10 to the negative 34th meters. To put that in context, a single proton is about 10 to the negative 15th meters across. The baseball's wavelength is nearly 20 orders of magnitude smaller than a proton. There is no apparatus, no slit, no measurement of any kind that could ever resolve a fringe pattern at that scale. The wavelength is there. It's just so tiny that it never matters. The same is true for the chair you're sitting in, the coffee on your desk, and the hand you're scrolling with. Each has a wave function, a probability density, and provided the object has a non-zero velocity, a wavelength. You'll never notice it, because at our scale, that density is so sharply peaked around a single point that having a definite location and having an extraordinarily narrow distribution are the same thing. The double-slit experiment is one of the few places where the hidden mechanics of quantum physics reach up far enough to see, and in doing so, exposes some of the strangest phenomena anywhere in modern science.